Hello, and welcome to CS 5:30 on Wednesday night. I see we have people still logging in, so I do want to go ahead and get started on time. I don't want to wait too long, so people should be making an effort to be able to log in on time. And I'm making every effort to be prepared to start on time, so that's what we would like to have as our goal. Hopefully everybody can, or at least somebody can hear me. Can I get response, make sure that this is working? Excellent. Okay, thank you. Okay, so do we have any questions tonight? Oh, I'm fine, thank you. So we're all being healthy and we're all being safe and everything is going well. I hope the same is true with everybody out there. Everybody staying safe and healthy and adjusting. And I know we'll still continue to make adjustments. It's going to be a little while before we get to a new normal. And I'm sure the new normal will be different than the old normal, but it'll be different than what today is. Okay, so you've been looking at the syllabus here. You can see that tonight we're going to be going off and discussing more about compilers. Taking a look now at the second phase of our compilers and going into more discussion, detailed discussion on that, see if we can understand that. I do want to share that I have decided, actually, I have, but I haven't decided. I've trying to figure out, I know as a reminder, next Monday is when, as you can see here, put my little pointer up. As you can see here, next Monday is when your big project is due. There we go. So that's when your big project is due. So I know some of you, most of you will probably be working through the weekend on getting that all cleaned up and ready to go. And so I'm looking at either the 22nd or the 27th, rather, either this next Wednesday or the next Monday for that mini exam that I was talking about. And I'd like to do it on the Wednesday, but you could also talk me into the Monday as well. So that's one of the things I want to finalize tonight is just decide on which of these two dates to do that on. It will be the online format. It'll be a shorter time allocated because it's just the one problem. So I will be setting it up for that. And the other thing is I have almost completed all of the scanning of all of the exam ones. I'm going to be finishing that up tomorrow night so I can get those distributed to everybody here either late Thursday or Friday. And that way you can see what you were struggling with there on problem number 6. And then you can assess that and use that as a study aid. So I want to get that out to you so you can be looking at this weekend and the couple days before Wednesday, if that's the date we settle on here. Okay, so I'm real close. I still have about a dozen exams here to hand scan because I don't have the super duper deluxe powerful automatic document feeder scanner that we have in the office, unfortunately. So I have a little scanner that I have access to, which is me feeding every page one at a time, which is taking a little bit of time, but you're worth it. So I'm getting almost there. Okay, so no additional questions. Thanks. I guess we will go back to the lectures. Okay, so make this larger. This is slide 28. All right. So as a reminder, we took a look at introduction to compiler structures. I lost my pointer. And we did an introduction, and then we spent some time talking about the lexical analysis phase of our compiler. So what we're going to do now is go into the next phase, which is looking at the syntactical analysis phase of our compiler. And as you might recall, we talked about this phase is going to take in as input those lexical tokens that I recognized and classified in the lexical analysis phase. And we're going to do our analysis on that, looking at syntactical meaning of what the input is telling us to see if everything was constructed correctly so that we can organize and generate code correctly based upon that input. So output of this phase is going to be either a parsing tree or a stack that has taken these tokens and generated this organization to them that's going to make sense from the way that we need to take a look at it to generate the code that's going to then make sense out of these different structures and algorithms that are being implemented by the programmers and be able to generate correct code that will execute. Okay, so go here and I'll make the screen larger, full screen, so you can see it better. There we go. Okay, so this is still considered the front end of a compiler, or a compiler front end. You might have wondered why I labeled the semantic phase A and the syntactic phase here B, and that's because they're both parts of the front end, but they have very different functions. Where the lexical analysis was looking at, again, the definitions to see if we could just recognize and classify basic fundamental parts of the code that was fed to the compiler. And now what we're going to do is we're going to organize it in such a way that we can start putting some reasonable sense of meaning to this so that we can generate correct code that will run correctly. Okay, so like we say in here, it's a parser. We're going to build a parser. It's a different kind of parser than what we're using in the lexical phase, because we're now using those tokens, right, that we generated in the lexical phase. And now we're going to use, because we keep talking about parse trees or stacks, we're going to use one of two different techniques for being able to do this analysis. One's a bottom-up process, and the other is a top-down process. And you'll see how that works when we start looking at examples here, and why we refer to the tree or the stack as bottom-up or parse top-down. Okay, so what we're trying to do here is we're going to apply some additional rules to the organization or the order of these instructions that the programmer put into the source code. Okay, so we're still going to use grammars for defining this, and typically BNF or eBNF will be the grammar specification that we're going to use to capture this larger construct. But what we're going to do is we're going to specifically look at things like the order of precedence. Order of precedence, as a reminder, of course, that is the order in which you want to evaluate these expressions that the programmer stated inside of the source code. So the order or the precedence rules are going to be defined, and we're going to look at some options, at some ways to define those precedence rules so that we can then apply that by analyzing the sequence of these tokens and reordering them as needed to enforce the precedence rules of that particular language and that grammar. Okay, so we're also going to recognize larger constructs. And larger constructs, as you can see here, is some examples of them are the bigger building blocks of the language, right? What is a statement? What is a subprogram call or a function call or a procedure call? What are expressions? And if you're doing structs and doing defines like that, you're also going to be organizing those and classifying those larger constructs now that you have these fundamental tokens that you have been able to regenerate classifications for and generate tokens with those classifications. So on the syntactical phase, that's what we're really doing. That's what we're talking about doing here in this phase is making a bigger construct recognition and classification from these tokens. All right. So we're going to use one of these two structures to help us organize those smaller tokens, if you will, more fundamental tokens, probably a better way to put it, into these larger structures. Too far. There we go. Front end and a very sensitive mouse, I guess. Okay. All right. So let's start with the bottom-up parsing approach. The bottom-up parsing approach is one where we're first evaluating operator precedence parsing, which means, again, that order of processing that we want to, or evaluations, probably a better way to put it, that order of evaluation that we want to perform so that we get the operands and the operators organized correctly for this particular language so we can generate the machine code. We're going to do this by looking at, and when I say looking at, we're going to get pairwise operations or tokens, and we're going to evaluate them pairwise, okay, by pairs. So we're breaking this all down to very fundamental things. We took this large source code file of what looked like human readable English for that particular language construct and generated these tokens in these orders that the programmers identified them in. But now we're going to take them by pairs and see if we can make some larger order sense out of these sequence of tokens that were given to us based upon the grammar specification. Okay, so pairwise operators, that's what we're really looking at here. And what we want to do with this is we want to determine which one of these operators needs to be evaluated first, so we know what the order of precedence is. And you're going to see when we get there that there's an operator for everything in the language, and we kind of take it for granted when we're learning how to program in a language and we're learning how to translate requirements into design and source code so that we could then throw it to the compiler to generate machine code with. But what we're going to do now is, from that level of thinking that you're used to thinking, that from a source code writer, we're now going to say, but what you were really doing was you were expressing these in terms of the language's syntax and grammar rules and all that, these operations that you want to perform. Even if it's a statement declaration, that itself is an operation. And so we're going to have to shift our thinking a little bit so that we're thinking in those terms now at the systems level, because we're going to generate machine instructions, or we're going to generate memory locations based upon what the code is telling us to do. All right, so that's a little bit of what we're getting into here. So we're going to use, for a bottom-up parsing approach, we are going to use what we call a shift-reduce parser, which is going to use what we refer to as an LR grammar. An LR grammar is a left-to-rightmost derivation grammar. As you see down here at the bottom, I went ahead and created these definitions for you because we were going to introduce some of these others later on, but just to help you understand why we have this language, the LR, left to right, rightmost derivation, okay, is the most fundamental one that we're going to look at here. We're also going to look at a variation of it as referred to as the LRK grammar. And what that is, it's also a left to right with rightmost derivation grammar, but it adds what we refer to as a K look-ahead value to it. Without the K, the LR would actually be written as an LR1, because what this officially is doing is it's a left to right, rightmost derivation grammar with a one look ahead value. So we'll look ahead to the next token to evaluate before we do the derivation. We have a variation of that LR grammar called the LRK, which allows us then to specify, oh, what if we want to look ahead 2 or 3 instead of just 1? There are some grammars where we will allow a K look-ahead value other than 1, and that's why we break that out and refer to that as an LRK grammar. And then later on, we're going to look at some other grammars. We may or may not get to these other grammars, but just so you understand that there are some other grammars out there that are specialized and they have very important purposes and stuff, but these are by far the largest grammars that are in use. So that's what we are going to focus on. See, we have a question, and what are grammars exactly? We are going to look at that. A grammar is the specification of this particular computing language with the focused on the higher level constructs. So we're now focused on the rules that define things like the precedence orders and what comprise statements and functions and a program, procedures, structs, all of those things are what we're using these grammar rules to define what these are and how to recognize them. So we're going to look at a special case of a grammar, most common one being the LR, or left to right, rightmost derivation grammar. Okay, and we're going to see later, a little bit later here, what those specifications look like. But for now, let's see if we can understand what we're trying to do with them. So in the context of this bottoms-up parser, which is an operator precedence parser, we're focused on the pairwise evaluation of operators and operands, and operators versus other operators is really the most important part of this precedence parsing that we're talking about. We're going to use the stack to help us organize these tokens and manage these tokens while we're trying to do this evaluation. Okay, so if we're looking at pairwise operators, there's these other things that are in the way, and we're going to use these stacks to help us organize them so that we can then evaluate one operator from the next operator, so we can then establish which one has higher precedence and needs to be evaluated first. That's our goal here. Okay, so a stack, obviously a stack, we have two operations that are very common to stacks, pushing and popping, right? So what we're going to do with our stack here is that as we evaluate tokens, if we have unrecognized tokens we can't classify just yet, we will push them onto the stack. Once the symbols are recognized by one of our grammar rules, then that grammar rule can reduce or pop that particular token or symbol or combinations of them off the stack. And what we'll do is replace those symbols with the rule name that evaluated that action, and then continue with the next tokens and so on. We are going to continue doing that. So Andrew asks, precedence like an order of operations like multiply is higher precedence than addition? Absolutely. So the arithmetic operations are pretty easy to recognize that we need to do those in a specific order, where multiply, divide has higher precedence than addition, subtraction. But we're also going to look at assignment operators. We're also going to look at parentheses. We're also going to look at semicolons. We're also going to look at function specifications, and we're going to look at these different constructs because that's what the grammar needs to be able to specify and recognize. And we're going to need to generate precedence rules for all of those operators, just like you pointed out there, not just those basic ones, but more complex ones as well, so that we can ensure that, yeah, we're doing these in the proper order, so that anything that's in a function block gets evaluated before we get to the next function block. Or anything in an expression gets evaluated before we go to the next expression, and so on. It's a great question. So I want to make sure we do understand these very fundamental concepts here that we're talking about, because we're diving into some details. And if we're not sure what we're really trying to do here yet, this is a good time to make sure we get that right. Okay. So now let's take a look at a grammar. Now we've defined a few things here. We'll use B and Fs, so this looks a little common little bit more readable to you now than what we were doing on Monday night. So you've seen this, but this is a little bit more complex. Now, some of you may have heard of, or some of you might even be familiar with the Pascal programming language. It is still in use today. Its primary purpose was that of being an instructional computing language because it's pretty easy to build, and we wrote compilers for these, and people write even real programs with them. But the main intent was to use it as a teaching language, even though you can write fully functional programs with them, and a lot of people did, and some people still do. So the nice thing is it has most of the basic parts of a language that even C, C++, well, it's not object-oriented, so it doesn't have the object-oriented components, but some of the most powerful languages today have a lot of similarities with this particular language. So it's very easy to comprehend and use that for an example like what we're doing here. I think you'll be able to understand this pretty easily. All right, so this is the grammar specification for the Pascal language. Now notice that we are at a different level. So when we talked about the BNF for the alphabet previously, that still has to be defined, but we already talked about that for the lexical phase of this tool. So we're not going to focus on that too much. We're going to be focusing more on, okay, this larger construct now, and being able to define the bigger part of this language now that we've recognized our alphabets and that part of it. Okay, so things like a program. What is a program? That's really starting at the highest level. So I'll start here, and then we're going to jump down to the bottom, because as you probably remember from Monday night, when we're constructing a BNF and evaluating a BNF, the most fundamental definitions are down at the bottom. Let's look at the high level first. I always find that interesting. What is a program? Well, in the Pascal language, the program is going to start with the reserved word program, which is going to require something called a program name. Now, as you recall, these things in angle brackets are rules, and these are the definitions of these rules. So we defined a program is defined to be this reserved word program, followed by a rule, prog name, followed by a reserved word var, followed by a a rule deck list, followed by reserved word begin, followed by a rule statement list, followed by a reserved word in, and a period. And as we talked about on Monday night, every character you put in this rule definition here has to be explicitly correct. If you put a period here, then every program must end with an end followed by a period. And we're going to see why we make that differentiation here later on. But this is very specific, and that's not an accident. It's not a typo. It's very specific. You have to have that in order to end and terminate your program. And then being able to, as a compiler writer, recognize that the programmer is at the end of this particular program, and there are no additional pieces to evaluate. All right, so that's what a program looks like. That's how, if you're writing a program in the Pascal programming language, you would construct it exactly like this. Of course, with these variable names here, you're going to, of course, break them down in these rules. You're going to break them down into other things so you can generate these higher orders of concepts, conceptual recognitions down to detailed specifications. And so let's take a look at that. Let's go down to the most fundamental rule, and that rule is that of the body. The body is defined to be something called a statement, or it could be the reserved word begin followed by a statement list followed by an end, no period. All right, so this is exactly why at the end of the program, the people who had designed this particular program wanted the end of the program to also have a period, so that it's very unambiguous when you encounter the reserved word that you are here and not here. Okay, so when you're thinking about designing a program specification, a grammar specification for your program, those are the kinds of details that you are thinking about in order to do this design. All right, so a statement is something that's going to occur fairly frequently. This begin statement list in, we're going to see that is a smaller construct that's going to happen somewhat frequently throughout the program, and we'll see how that works here very soon. Now, it's also probably worth looking at, although you probably are looking at, the tokens that are unique to Pascal, right? And we have the reserved word list, just like we talked about before. Notice we have the end and the end followed by a period as two different tokens for that very reason we talked about. Integers for read, writes, to, do, and then these are all comma separated lists. The different identifiers that it can recognize and classify and use. Notice that we're going to use div instead of the slash sign for the division, and IDs and ints. IDs and ints are what are going to be defined in your alphabet, and those are the standard IDs and ints that you're used to from previous examples. Okay, so that's the body. Index expression is defined to be an ID followed by a colon equals, and we saw colon equals down here as a token, okay? ID followed by a colon equals, followed by a rule expression, followed by reserve word to, followed by an expression rule. So this is where we're doing the left-hand rule, right-hand rule definitions for an assignment statement, right? So an index expression, that's where we're doing these assignments. That's one place where we're doing these assignments. So I'm not going to go through all of these, but there's a few novel ones. This one here is easy, a for do loop. Reads and writes. Notice that both reads and writes, and these are kind of clearly named rules using the reserve words, require an open parentheses, space, and an ID list, and space, and then a closed parentheses. So even though we didn't define a space before, we are going to require it here. Okay, so it's going to be part of the alphabet. We'll define space as part of the alphabet, and we're using that here very explicitly. So if you're doing a read or write, you're going to need to use the parentheses, and your ID list will be inside the parentheses preceded with a space and a space as its antecedent. Let's see. Another thing that's interesting is, I'm going to jump around a little bit here. We looked at ID expression where we said it's defined to be an ID followed by this, followed by that. Notice that up here in assign, we also have a case where assign is defined to be an ID followed by a colon equals, followed by an expression. Okay, so what this is doing is it's creating this rule assign, which is similar to the index expression, except that in index expression, you have the ID colon equals followed by an expression, but is also followed by the reserved word to, followed by something evaluated as expression. So if you don't have that, you have just the ID equals colon expression, we have another rule up here, the assign rule, the assignment operator, which allows us to do exactly that, create an assignment by doing an ID colon equals followed by an expression. Now you have an assignment. But this gets even better, right? Because we have ID also defined in an ID list, where we can have an ID by itself, not followed by a colon equals, or we can have something called an ID list followed by an ID. All right, so there's ID showing up in another place. And oh, looky here, where we have prog name is defined to be just an ID. Well, we're going to need that for this prog name here. So ID itself is a very fundamental concept. And so things like a program name, that is an ID, that's very simple. It's by itself. It's not followed by a colon equals, right? Because if we had a colon equals, then we need an expression behind it, or we need an expression followed by 2, followed by an expression. Or it could be an ID by itself that's then going to get further classified with something that's using an ID list. So what's using an ID list? Well, reads are using ID lists. Writes are using ID lists. So if we're using ID lists there and there, it could be used in these places. Okay, so when we start thinking about building a parser that can implement a grammar like this, we have to look for these kinds of situations where a token that we classified as an ID could be classified in multiple different ways depending upon what's next to it. And this is why it's important to look at all of these things pairwise to find out, how do I want to classify it? Which one of these rules is going to classify it? Now we also have ID show up in another one. You'll notice that I have 3 rules here that I put into blue. I put them into blue because of this very reason. These 3 rules here are what's really establishing precedence for this language. Okay, there's a couple of precedence operations going on here, like with the read and the write. There's some precedence work going on there, but it's unambiguous. It's very clear. There's no way to misinterpret these orders of precedence where I have to have an open parent followed by an ID list followed by a closed parent with the space in there. I have to do it in that order to recognize and classify this as a right rule. But here it's much more flexible. And so it's worth taking a look at. So let's take a look at the first one, factor. Factor is defined to be an ID or an int, or it can be open parent, space, expression, space, closed parent. It could be any one of these 3 things can be a factor. So that's another place where we can define ID, where we can classify ID without, and here an ID list is different from this ID right here because it's not followed by a colon equals, but it's probably going to be followed by something else. What? Let's take a look at it. All right, so what uses factor? Term uses factor. And so term is defined to be, or it could be a factor. So an ID, a term can be an ID, a term can be an integer, and of course a term could be this parentheses expression parentheses. Any one of those things. But it's more interesting when we're able to build something larger out of this term. So the first thing we'll do is if it's an integer, ID or an integer, and we classify it as a term because we're not classifying it as an ID list or as a prog name, then we could precede it with either a multiply or a divide, right? Because we have factor, we have a term, so we have a term that we classified as a factor here. So the term could be here, and if it's followed by a multiply and another factor, which was an ID or an integer or this expression in parentheses, or divide followed by an ID or an integer or something in parentheses, an expression in parentheses, then we can classify it as a term. But we're not done because that's just those 2 arithmetic expressions. But we can do that, and we would do that first if we could. If we can't, then what we'll do is we'll classify something, one of these IDs, integers, or an expressions inside of parentheses as a factor, and we can recognize the factor and classify it as a term. A term by itself could also be evaluated as an expression, but if it's followed by a multiply symbol or the div, reserved word, then we're not going to evaluate it as expression. We'll evaluate it as a term based upon this rule or this rule. But if it's not that, we can evaluate it as an expression, that term as an expression. And if the expression then is followed by a plus or is followed by a minus, and each of those is followed by another term, which was a factor, which is an ID or an integer or an expression inside of parentheses, then we can evaluate it as an expression. So writing it this way, where we can recognize an ID or an integer or an expression in parentheses as a factor, and then factor gets evaluated as a term, and a term followed by one of these, that's going to get evaluated first before we would classify that term as an expression, and then look and see if it's followed by a plus term or a minus term. Can you see how that is forcing the operations, the precedence of these operators here over these here? Any questions on that? That's a very important and also a very powerful concept, and how we can really implement that complex concept to realistically enforce those rules of precedence by evaluating these terms over this manner, one before the other. Sure, I'd be happy to. We'll have some examples coming up too, which will make it help. But let's see if we can take a look at this another way, right? So the most fundamental thing we have are IDs and integers, where we can recognize these symbols and be able to use them as variable names so that we can then do operations on them. So we take those fundamental operators, these IDs and ints, right? We've defined those here, and this is the first place we're using them. Ignore this ID for now. This is the first place where we're really trying to use them, where we're trying to use them in an arithmetic way to show us how we can then generate grammar rules to force this operator precedence that we are so dependent upon to get the right answers. All right, so IDs and integers, most fundamental things, and we're going to include the expressions in parentheses. I'm going to leave this out of our discussion now just to keep it simple, but it's in the same level as these fundamental IDs, which is like a variable name, in integers, which is a number, of course. Okay, so if we encounter a symbol that's an ID or an integer, we'll classify it as a factor. Assuming it's not these things, we're beyond that. We're going to say we're here. Okay, so we get a number, we get a name, we classify it as a factor. Now, the fact that multiplies and divides have higher precedence in the evaluation order of an expression than pluses, additions, and subtractions means that we need to do those pluses and, multiplies and divides before we do the adds and subtracts. So we need to do that. So we'll classify these fundamental variable names and numbers as a factor. And then the highest precedence that needs to take place is multiply and divide. So what we'll do is we'll take the factor, and we've recognized it, so we'll classify it as a term. I've now got a symbol name, I've now got a number, it's not followed by an equals, a colon equals, it's now a term. So I classify it as a term. Yes, a term can be classified as an expression as well, but let's just hold it here first, and let's see what's coming next in the sequence of things that the programmer had specified. So if the programmer had written a variable name followed by a multiply followed by a number or another variable name, then we've classified this factor as a term for that first variable name, and now we have following it a multiply followed by a number. Okay, so if we did that, then we would say, a multiply is an ID. Okay, well, no, it's not an ID. Excuse me. Do not take that as an ID. It's not an ID. That's not a symbol name. It's a multiply symbol. So it is a keyword. And so it's a keyword multiply followed by a number. Well, a number can be classified as a factor. We already have a term. So we have a term now followed by a multiply token followed by a factor. That was that number that was classified as a factor. We could now take that term that we had previously classified as a term, followed by this multiply token and the factor that we classified for that number, and now accept that as a term. Having done that, we've taken that symbol name, we've taken that multiply token, and we've taken that number, and we've classified them now as a term. That means we're going to do that operation before we do anything else. We can't say, oh, but it could have been an expression, that factor could have been an expression. If it was followed by a plus token and another term, then we could have done that. But we prevented that from happening because we constructed this grammar such that the term would get classified before an expression would get classified. So a term would recognize that multiply, that term that was followed by the multiply symbol followed by a factor, and perform that operation before it would try to even classify it as one of these two. Does that make sense? Okay, so we still want to recognize plus and minus. So that's why if it's not followed, if that term, that symbol name that we had that classified as a factor, that got classified as a term, if it was not followed by a multiply factor or a div factor, then yeah, we would go ahead and take that term, classify it as an expression. If it was followed by the plus token followed by a term, we can still do that, but we would have checked for a multiply first and a divide first. So some would think of this as going backwards, but it really isn't. That's why we're using the bottom-up approach, using the stack. We're going to keep pushing things onto the stack until we can evaluate something. As soon as we can evaluate the sequence of tokens sitting on the stack, we're going to pop them off the stack, and we're going to put first this factor in place of this ID or this int that we recognize, and put the factor in its place so that on the stack, and I've got an example that'll show this here shortly, so that we can then further classify it as a term and then recognize it as a term followed by a multiply followed by a factor, and then classify that as a term, and keep continuously doing this until we get to the end of the program. So Andrew's written an excellent description here. And the question is, so given that thesis there requires a second argument to evaluate it as a term, yeah, that's correct. So the multiplication division has to happen first because it's doing that combo of term followed by a multiply symbol followed by a factor, the factor being this, right? Yes, that is correct. So the idea with the stack is we're always looking for a rule. Anytime we push something onto the stack, remember this is also a look ahead one. We haven't talked about how that works yet. This is just the concepts of the grammar. So we're talking about the mechanics of it. I've got an example that will show you and hopefully make it easier to see how we would mechanically actually construct this. But this is the concept of operations. But it's important to get this because go to the mechanics is just going to see this is how you can build it. whereas the concept, so that you can write your own grammar specifications or you can assess somebody else's grammar specifications so you could then understand their grammars, is important. For example, if you understand how this is working and how this is going to get classified as this rule, which can be used here, and classified as this rule, which can be used here or here in the same rule, that's the important part that we're talking about here. Because we could have substituted these. We could have said plus and minus here, and we could have put the multiply symbol, the asterisk, and the div here. And what that would have done was just kind of turn your world upside down, because that would have said we would have evaluated a plus and a minus symbol at a higher level of precedence than the multiply and the divide. And so if you were trying to write code to do an arithmetic expression, it would probably be incorrect, because when you're writing it, you are taking into account the order of precedence for that particular language's grammar specification. And most of you are scratching your heads and saying, oh, I just assumed that when I learned any of the languages that you've learned, like Java and Ruby and C and C++ and all these languages, that was the order of precedence. And at that point, you were very likely making an assumption. Fortunately, it was a correct one, because that is how most languages, but not all languages, construct their orders of precedence for arithmetic expressions. But they don't have to. It's only because the grammar specification states something like this for that particular language that it is being evaluated that way correctly. The other would be correct too. It's just that your assumption would be incorrect. Okay, we think we got that. Other questions on how this works? I want to make sure we understand this concept before we go on. Okay. So now let's take a look at the mechanics of how we could do something like this. Okay, so we're going to depict our stack like this, and we're going to try to evaluate some token stream based upon this grammar specification here, using an LR grammar to implement. All right, so there was some code before, there's some code after, but at some point here, we encounter this reserved word, begin. Okay, and we're also, if you're looking ahead more than one, this is an LR1 grammar, so we're going to see, oh, we've got this token begin, and the next token is read. And so based upon that, where do you think we are going to likely want to start trying to classify that begin reserved word? Body, correct. Down the body is where that reserved word begin is used. Scanning your code up here, yeah, begin could be here, and we said there was some other code preceding it, so it is possible it is here, but it's more likely going to be in this body here. So this is probably where it's going to try to get classified. That's probably where we want to go. We don't see begin reserved word used anywhere else in this grammar specification. So that's probably where it's going to be. I say that now because it's always good when we're looking at understanding how these tools are working, that we keep kind of in mind the big picture, not only of what the tool is doing, but what our example is doing too. All right, so we encounter begin. Now notice I have the pointer. The pointer is where we currently are trying to evaluate. So we have that reserved word. So we could not classify it by itself. So we're going to do a shift operation, which will push it onto the stack. And so you saw that happen here. So what we're going to do is do our one look ahead, and it's read. Okay, and read itself also cannot be classified by itself. So we're also going to do a shift operation, pushing it onto the stack. Do a one look ahead. We have the open parent now. So the open parent, we don't have a rule that can accept it by itself. So we're going to do a shift operation, pushing it onto the stack. Now, let me back up here for just a second. When we did the one look ahead here, we're looking at the stack and we have a read preceded by a begin, but we don't have a rule that can accept that, not by itself. So that's why we're doing that one look ahead. So we do the shift operation, we do the one look ahead, and we have an ID preceded by an open parentheses. And no, we don't have a rule that can accept that. So we do a shift operation, which pushed it onto the stack. We now have a closed parentheses. Closed parentheses preceded by an ID. By itself, it doesn't have a rule we can evaluate. However, if you go back to the ID list, it says, oh, wait a minute, we can do a closed parentheses preceded by an ID and generate a rule called ID list. So we say that's a rule that we can generate, this ID, if it's preceded, this going to be this closed parentheses, if it's preceded by an ID, it could be an ID list. Okay, so we classified that ID as an ID list, but now we still need to push this closed parentheses onto the stack. And then do our one look ahead. And then ask the question, oh, I have a semicolon. It's now preceded by a closed parentheses ID list, open parentheses, read, begin. How much of that can we evaluate? It turns out that a read can evaluate the read, open parentheses, ID, close parentheses. So we popped all of those off of the stack, and then we pushed a read onto the stack. And then we would push the semicolon on here to say, hey, is there a rule that can recognize a semicolon preceded by a read, preceded by a begin? And if so, we would classify that. Otherwise, we would take the following tokens and just continue in the same manner, pushing tokens onto the stack based upon the evaluation of those tokens and the grammar rule specifications that we were using for evaluating the sequence, that order of tokens that we are using the stack and the grammar rules to evaluate. Yes, the question is, I didn't recognize ID list. Can we go back and look at that rule? And the answer is yes. So here you see the ID list rule is defined to be an ID, which we had. It could also be an ID list followed by a comma followed by an ID list, which is a colon separated list of IDs, right? Which we do with like variable names. When we're trying to create a variable and a list of variables, we can do that, right? Ah, you're quite welcome. So that's how we can recognize an ID, the fundamental token, by itself and classify it as an ID list. And here is the read rule, which had read followed by the open parent, followed by the ID list, followed by the closed parent. So the important thing I think to point out when we were doing those evaluations is that we're always doing that one look ahead. When we're looking at that next token, that's when we're looking at what was on the stack. So that's where when we had pushed this second closed parent, we were doing the one look ahead on the closed parent and saying, hey, an ID list, that the one rule in here that would accept a closed parent preceded by an ID would be an ID list. So that's why we classified the ID as an ID list at this time. That was the reduction. And then we still had to push that closed parent by a shift operation onto the stack because we still couldn't evaluate the parentheses, the open and closed parentheses with the ID list in it for the read rule until we push this on the stack. And since this is a k equals 1 look ahead, we're now looking ahead at that semicolon to say, can we further reduce the stack? And the answer was yes. These 4 here were part of the rule, could be evaluated rather by the rule read. So we then pop, 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 and then push read. So when you're asking, would it always explicitly say ID? In order for an ID list rule to recognize a token, that token has to have already been classified as an ID. Because back at the ID list rule, it must be an ID. An ID list can, so to take an ID by itself can be recognized as an ID list, and then we can just do this comma separated list of IDs using this rule here. So yes, it first has to be evaluated as an ID before, and that's done at the lexical analysis phase before we can get to this tactical here. Sure. And Andrew, your comment is excellent. Yes, we want to, so if you're not reading there, the question is, do we keep popping off until we can't evaluate any further? And the answer is yes. We want to use the rule that can accept this or as many of these tokens in this order as possible. So if we had 2 rules, if we had one rule that could, and we didn't in this grammar, but if we had one rule that can accept the open parent followed by the ID list followed by the closed parent, and another rule which can accept a read followed by an open parent followed by an ID list followed by a closed parent, we would want to use the read rule. Now it's better to write your grammar such that you don't have that kind of ambiguity in it. And that's one of the cool things about the Pascal grammar is it is completely unambiguous. There is no ambiguity in that grammar specification. This is the only sequence this could be evaluated at. And so it would pop off all of these looking for the largest rule, and it will be very clear in this manner. Good question. What happens when we get down to read? Notice that when we started this evaluation here, the stack was empty. Well, in reality, it would never be empty, because if it was empty, then that means the very fundamental token that would be at the very bottom of the stack would be the reserve word program. Okay, so in order for us to evaluate a program, it's going to have to start with this reserve word program, and that will be the very last thing popped off of the stack. So in this example here is really kind of a misnomer because there's other stuff on the stack that we're not showing. The question is, how do we recognize the begin itself and be able to pop it off the stack? That's where we go to, well, it has to be something like this then. It's going to have to be a begin followed by a statement list followed by an end. So the follow-on code here is going to have some code that would get evaluated into a statement list, and then a reserved word end in order for us to be able to pop off that begin that you saw at that stack. Okay, so that's also, Austin, a very important question to make sure we understand this conceptually as well. So the question is, does ID have to get pushed on? I'm going to rephrase it. Does the ID have to get pushed onto the stack, or could we just put an ID list on the stack? And the answer is no. We have to be very strict in our evaluation of these tokens. We're going to push every token onto the stack and then evaluate. The ID, the reserved words were defined by the language. These symbol tokens here were defined by the language. ID was defined by the language, but it was implemented in the lexical phase. So coming into this phase, it's as fundamental as a reserved word or a symbol. So it has to be pushed onto the stack before we can evaluate it. So we can never evaluate ID as we're scanning it here and trying to push it onto the stack and saying, oh, it's an ID, let's just make an ID list and push that onto the stack. No, that would be a special case rule, and we do not want any special case rules. We want the algorithm to work exactly the same for every token it encounters, and we want the evaluation to be done as a one look ahead. We're going to look at the next token. As we're looking at the next token, we're going to try to evaluate as much of the stack as we can. Does that make sense? So there, in that example, we did shift the ID because we're not evaluating it. We, in fact, had done a one look ahead at ID and said, I don't have a rule that can classify this preceded by this, so it pushes ID onto the stack. And then we increment the pointer and we said, wait a minute, we could now classify it as an ID list because we now are looking one ahead and we can say we have an ID. ID can be reduced, recognized by this rule ID list, and replacing ID with ID list on the stack at this time. Dante, you said it very well. Yes. We do the one look ahead, try to evaluate. We then push that token onto the stack, do a look ahead one, and now evaluate the stack. Exactly. If we can pop off the stack and do a reduce, we will. If we can't, the order doesn't support that, then we have to push this on the stack, do another k equals 1 look ahead, and then see if we can evaluate what's on the stack. And so algorithmically, that makes sense, right? You can build an algorithm to do that very specific thing, and trying, and by postponing, if you will, the evaluation of what you just pushed onto the stack in that sequence like that actually makes it easier, and it also makes it less error prone to build software to do exactly that when you do it in that order. And yes, exactly. The look ahead is how we keep evaluating things on the stack until we pop it off. And for those of you who are thinking, wait a minute, what about that LRK grammar where we do a look ahead 2 or look ahead 3? Yeah, that's because some language types, it's actually, you can actually construct grammars such that you can do look ahead 2 and do a better evaluation than a look ahead 1. Most of them are 1. And this is why. You can, especially if you're working with unambiguous grammars. If you're working with ambiguous grammars, typically you want to do k equals something else, or you want to use another kind of grammar. But let's not worry about that. I'm not going to test you on that. What I will be testing you are the LR grammars and a little bit about LRK. So LR being LR with K equal 1. And you got it. Okay. Other questions? Yes. So K is the number of look-aheads. Without K explicitly being stated, K equals 1. Look ahead equals 1. Okay, making sense? Not so scary now, right? 1 meaning looking ahead, 1 position ahead. Okay, any further questions? Exam 3 here. Well, no, mini exam 2. Here we come. Yes. Oh, I see, because this content will be on exam 3. Now I think I understand your comment. Yes, you can take this right to exam 3. This is very unambiguous, very clear. I think very clear. Hopefully it's very clear. And do read Dr. Beck's words in the textbook too, because he explains them a little bit differently. And if you can understand it, explain it in a couple different ways, then you understand it better. If you have general questions about program 2, I could take them now, email anytime. Exam 3 will be generally the same format as exam number 2 is correct. Okay, I guess we will, is assignment number 3 still planned? Absolutely. And I will be posting that. I'll probably go ahead and post it Sunday, even though you're finishing up assignment number 2, not due to turn in until Monday. A lot of you will probably be turning it in Sunday anyway, but I'll go ahead and post it Sunday so you have a chance to look at the assignment number 3 before we, as we start up a lecture on Monday. And the updated SDD for assignment number 2, if you have changes, absolutely. The idea with, yeah, exactly. So I expect as you're doing your coding and you're doing development of the project, you probably made some changes to your design, which are captured in your SDD. And so I am expecting that to be updated to reflect any changes. If no changes, then you should at least annotate that there were no changes. That would be very surprising to us to see, but it is possible. So be very explicit when you turn in your project that the SDD has been updated and here it is, or there have been no revisions. And yes, you will turn in the project on Blackboard. So for the code though, you want to leave those, also want to leave all those files in one of the person's You're selecting one of your teammates to be the person who turns in the assignment on Blackboard. It should also be in their Edoras account. Assignment 2, I'm pretty sure I set that to be at the start of class, which is 17:30 on Monday. All right, you're all quite welcome, and I wish everybody a great weekend. Stay safe and healthy, all those good things, and best wishes on finishing up this assignment. Okay, out here.